Hey everybody, Mr. Brennan here for day 2 of Festive Fractals. Today is the final space launch, so let's get right into it. Your questions were amazing yesterday. You're getting so good at the depth of your questions, the things you wanted to know about. Some are easy to answer, like Xander asked, what other shapes could be made into fractals? And so we'll talk about that too. Tomorrow especially, I'm going to blow your minds. You're going to make your own fractals if you finish today. And it's also going to be part of our contest reindeer games next week. So any shape, that's the answer. It's self-similar, repeating patterns that go on into infinity. So any shape can do that. Why is it called a tetrahedron? Tetra means 4. There's 4 faces on this. So lots of great questions. But these are the questions that came up lots of different ways. And I kind of put them all in one scenario. So given the average Christmas tree in Chimicum is about 7 3/4 feet tall, and that's pretty close. How many unit tetrahedron, how many of these guys would it take to create a tree that was about the same size? So that's where we start. How many iterations is that? Remember, an iteration is a generation. Like here's 1, this is our first one. Here's 2, here's the second iteration. Here's 3 iterations. So that's what that means, and so you got to figure that out. The math is not that hard. This shouldn't take you there very long, but it's really fun to think about. How much space would that take up on the floor? That's going to be the area of this space, and kind of getting to Rosie's question about how much space there is in the middle. It's 3/4 of this. If you know what this space is, you know that this is times 3 of those, or the space of all of this. Every time it's going to be 3/4, meaning 1/4, 1 out of 4 of these triangles is cut out on each face. So that'll be fun to think about. Then we get to the volume. I'm going to spend tomorrow talking about volume. How much space is this taking up? A 2-dimensional face and a 3-dimensional volume. So here's a 2-dimensional representation. This is a 3-dimensional representation. So I want you to create a table to help answer those questions. In this table, I already did the first 2 for you. You're welcome. I know they were very easy, but I wanted to show the first iteration has 1 total. How tall is it? 1 unit. And how tall is that really? I'll show you the math in a minute. It's 7 3/500 centimeters. So this is the second iteration. It's the second iteration. It's got 4 total units. You could see it's 2 units tall. If I was drilling right in the middle of those guys, it'd be 2 units tall. And so that's double this, so that's 14 7/10. The last thing I want you to do is make a graph, and how the graph you make is up to you. You're looking for relationships of numbers, so I would make several after I finish my table to answer this question, and then come up with something interesting. So we only have a couple minutes here, so let's talk about the relationship that we probably already remember from 4th and 5th grade of the area of a triangle, this part here, compared to the area of a parallelogram. Any triangle that I make, I can double it and it'll turn into a parallelogram. Kind of cool, huh? So I know that a parallelogram is just base times height. So to figure out a triangle, I just need 1/2 base times height, or base times height over 2. Same thing. So I know that the base is 9 and the height is 7.8. And so I multiply those guys together and I get 70.2 divided by 2 equals 35 1/10. So I'm going to cm squared. So that's the area of the triangle. As far as the volume goes, I think we're going to have to save that for tomorrow. And so we'll get to deal with question 3 later. In the meantime, please watch the video about the Menger sponge. You don't have to watch the whole thing. It's a little bit long, but it's going to blow your mind. So I hope you have a great day doing math. See you tomorrow.